Hi, welcome back. So we're in chapter 3. You must know the outline of derivatives and integrals. I think one of the most, and if not the most important subject of all time, if you would like to really master the use of mathematics as an independent language, is to understand both perspective of derivative and integrals of a function. Let's first of all consider the idea of having two variables of x and y, somehow in two dimensions. So we get like something in R2 or whatsoever. And we wanted to capture the relationship between them, and the easiest way to see it, for example, through a relation of a linear one. So linear means what, as we have seen before, that as the change of y goes on this direction, we also were measuring the change of x at the same time. So we quantify this change on something called the alpha, or the slope of this line. And we know, since it is linear, it should be always constant. Our actual challenge started when we have this case. For example, let's say I have this equation here. Let's call it just y is equal a quadratic equation of the form of x squared. Now here, if I want to follow the exact same procedures or the framework we did before by taking a point here, let's say, for example, this is my P1 here, and a point here, let's take in my P2, and I want to capture the slope. Previous procedure, just take the two coordinates, subtract from each other at the point of x and y. I'm not going to get actually exactly an alpha. I'm going to get actually a slope of a line. It's going to be what's called a secant line. And why it's secant? Because it will be passing through both points. And this kind of secant line, it just captures the average alpha. We have seen a way to capture actually the tangent line. So what is the best things to do? How about if I take a very small step away in a positive direction from this point and in a negative direction from this point? So in other words, let's say, for example, my P1 is just equal to x1 and y1. This is my original point, right? I'm going to define a step. I will call it h, and it's going to be a very, very small step, and I'm going to add it to the value of x. So I will have now x1 plus this h. Let me call this k plus. I'm gonna also take it to be subtracted from the same exact value of x, and then I will get k minus. So one is in the positive direction, one is in the negative direction. What would I do? I'm gonna take this two value of x, just inject them in the equation of this line to get the new values of y. Finally, a point, we call it k positive, which is this value here. And let me call this is the y, the new value of y, right? Get a new one, let's call it k negative, and a new value of y, let's call it y minus. Then I'm gonna apply the exact same procedure what I used to do by taking just the difference between this plus y minus this new y and the k plus minus the k. I will get now a value. Now this value alpha, it will be the slope of the tangent line passed through this point. How about if we try to do this at different levels? Now, how many kind of equation we've learned so far? I think we've learned all kind of equation that we can think. We've seen linear equation, we've seen constant to a certain indeterminate, and we say indeterminate to a constant power, like in this case, a log function. We're gonna do this actually mechanism, what I have done here, at every scenario. Let's go ahead and now draw the quadratic equation. You could say, I would like to get a tangent line to this point or to this point. And the quadratic equation, I have already written it, is 3 to the power of 2 plus 5x minus 10. So we're going to print the coordinate, define a very small step. And let's just start with this big step. So first of all, right? And then we got now two new values to the quadratic equation in a positive direction, negative direction, and the rest of the steps are the same. So let's go ahead and run this code and see what we get. So we get 2 and 12, which is this point here. So let's see now, I just add 0.10. It's quite a bit big step actually but let's see what the slope looks like. So I add 0.10 to the 2, and subtract it, and then I plugged in and I get two new values, subtract from each other, and get the slope from the positive side was 17.29 and from the negative side was 16.70. So there is 0.5 different between them, so they are quite a bit different. How about if we manipulate the step to be smaller? So you could see now the difference between both of them gets smaller and smaller, so it's 0.06, is almost zero. That means the slope of the line at this point 2 or 12 is going to be actually 17. Let's actually go ahead and try to write a line, exactly the tangent line. You could see it just passing through particular point on this line equation. I've done this for every possible scenario: linear equation, quadratic, when the base is constant, power, for example, e to the 7th power, the logarithm function, the absolute value, also take a function to a certain fraction. So each one of them experience by yourself. The simplest way to encapsulate all this mechanic that we were doing manually into a certain formula by taking the power, the largest power, and just subtract it from 1 and get the power to be the base. So this is the exact thing we're going to do. We call the power technique. So here we got a power of 1, right? For this indeterminate. So we're going to say 1 multiplied by x1 minus 1. Any constant in this case is going to take the value of 0. So this is the derivative of this function. That means if I am interested to learn about the slope of the line for a particular point, I just need to plug in the value of the x and I get it. Let's go ahead and explore the meaning of integral in the next section. Say, for example, a distance problem. Usually, to capture the meaning of distance, if you would have a certain object and you know the object had a starting point, position of 0, for example, and this object had this motion of movement. Now, I'm not considering the directionality of that, etc. But just let's drop that factor for now. So if this object has moved from position to a second position, let's say position number 1. Now, it is obvious that we could have here a distance. Now, the distance, it could be expressed in a certain form. For example, I could express the motion of that object in terms of a time. Could say the d can be expressed by some alpha in terms of the time, right? In other words, we could have said also the function of t is equal just the alpha t. What is the outcome of such calculation? You will get a certain quantity. Quantity could be a meter, for example, could be centimeters, could be kilometer, could be mile, could be anything, right? That express the meaning of a distance in a way that we can understand. There is another way also of looking at the same problem, the way how the object has moved from position 0 to position 1. For example, I could consider the speed. So I have now a new element. So this alpha actually could be a representative of another function that I'm talking about, which is representing the speed. So here I have a rate of a change. Graph that speed here in terms again of a time. Perhaps I could have a constant speed, or maybe I could have a speed in a linear constant, so it grows over the time, or also could have it in maybe a quadratic form, a cubic form, whatever. But the point is, I know now that the distance is expressed in terms of this speed. Now the question is, how can you quantify this line, the y here? This one is going to be justified as a rate of a change. So I could say that is a meter per second, or maybe kilometer per second, mile per second, etc., etc. So you could see the difference between the way we quantify this speed, which happens to be kind of an alpha here, in terms of the time comparison to the solid distance. Once again, how about we strip down the speed again? If I know the object was speeding from this point to this point on time, was it changing something related to its acceleration? So sometimes imagine this one at this point here, like it was like, say speed up and slow down again, speed up. So this is related to the acceleration. Acceleration can again be expressed like y is just equal some alpha by the t again. So I could again draw something related to the acceleration, could be constant again, could be linear, could be whatsoever. But this acceleration happens actually to represent exactly what you think, this alpha, which was actually related to the speed, and the speed represents this alpha, which is actually delivering distance. Quantity of this acceleration in terms of the y, once again, could be expressed as a meter per second, maybe a kilometer per second, a mile per second, doesn't matter. So we have defined kind of a distance, right? And then we expressed the distance maybe in a form of a speed, and then finally the acceleration. If you would have a function that give you the calculation of the distance. I will call it f of x. Now, if I take a derivative of this derivative, it will lead you to capture the speed. If you take one more derivative of this derivative, I would make a double. We're talking about the acceleration. Now, if we go backward, if you take the integral of this function in terms of this x, I am talking about getting back the rate of a change of this particular function. And if you take the integral of this back again, in terms again of the dx, you are getting to the actual distance that being cut. Consider, for example, this graph in here, the velocity. This particular function is telling you the rate of a change. Now, to take the integral back of this function, it will look like this, but this time this is going to be the exact distance. It should be in the form of a square if that was linear. So, for example, if I would have to ask you here, knowing the velocity, imagine in 3 minutes how much distance this object has traveled. So I'm asking you to answer me in terms of this function. In other words, as if I'm asking you what is the actual area of this triangle here, and I get the value of y, it will be exactly equal to the area that I have just calculated in here. And next, maybe we can have some practical examples, both derivative and integrals, into real life problems. And that's exactly what we're going to do next. I'll see you then.